All right, so let's get started. So, just as a quick plug, so if there's anything that you liked about this course, I do teach 2 other courses next semester. One on the simulation, but it's actually surprisingly similar to IEE 477, but it was already on the books in sustainability where I'm jointly appointed. It's a 212. But we cover basically the same sort of stuff that 477 does, but we also add a few things in the end, like chaos and tipping points and bifurcation analysis. So if you know of anybody who might, this might still fit into somewhere that would work on their schedule and are looking for some other sort of simulation type course, there's that one. Those of you that are in the kind of the 4+1 might be interested in this seminar that I'm teaching on bio-inspired AI and optimization. So meta-heuristics, a lot of people hear about, but maybe don't understand how they work, like genetic algorithms and simulated annealing and particle swarm optimization and those sorts of things. So types of ways in which we can effectively use simulation to do optimization, as opposed to the other things that we've talked about, which are optimization methods for optimizing sim. So how do you simulate a group of agents that act like genes, and how does that end up solving an interesting problem for you that might help you optimize your jet engine, for example. So those are sorts of things that we would talk about in those sorts. So if you happen to know anybody who that might still fit on their schedule, it's actually, there's, I think I have 43 people signed up for this course. If I get to 50, I get a TA, so that would be kind of cool. But otherwise, we can do it without a TA as well. So, but the basic for this course, the way things go is this week, we have this sort of quick wrap-up lecture, should be probably shorter than normal. Then we've got the lab section before the Thanksgiving break is just an open lab that you can, sort of one of the kind of last minute times for questions, the sort of formal times. Then there's Thanksgiving break. Then going into next week, we'll start with lecture M, which is a final exam review lecture. It's very similar to the midterm review lecture. So the slides will basically be sampled from the previous slides, maybe with a few like what were the main points for this lecture or this unit type slides spliced in. There is this practice ICAM part B that is due before that lecture. That's one of the ones that samples from all the other ICAs. Then there's going to be these practice ones that aren't for a grade, but if you want those ICAs to sort of have available for you to keep practicing for the final exam, those are available. There are practice exams available, practice problems on Canvas. And then so this is kind of new. So initially the plan was for everybody to do their presentations in their lab section on Wednesday. But recently we've been getting a lot of pressure that as soon as next fall, they'd like to have 475 available for an online industrial engineering degree. And so I've been trying to rapidly experiment with things that would make that rapidly possible. And one of the things that kind of the sticking points has been these presentations. And so what I'd like to experiment with this semester, and I'm just hoping that this will actually be preferable for a majority of you too, is that rather than having you present in class, then with your groups by 5:30 p.m. on Wednesday, so not tomorrow, but the Wednesday where you would have normally presented, we'll have you actually upload to Canvas your 10-minute presentation that you can use however you'd like to record it. So you could just be capturing, like I do on this one over here, you could just be capturing slides with audio overlay, you could be capturing video, however you would like, and then those 10 minutes will go up. And then I still want other people to be able to see your presentations, and so I've rigged Canvas for peer reviews, which is also new for me, so be a little bit of an experiment. But basically, after you upload that, the due date at 5:30 p.m. will pass, and then Canvas will automatically assign 3 other groups to you. And so between then and Saturday night, when your final report is due, you watch 3 other groups' presentations, you click on a little rubric that I provided, and make sure you only click save when you're done, because it gets a little complicated if you sort of save prematurely. And you can add a couple of comments, and then what that will do is I will take all of your collective evaluations plus mine, and that will go into the scores on the presentations. and then your participation in the peer review will go into your scores on the attendance. So then that's how you get both of those, your presentation score and your attendance score. So everybody's still seeing at least 3 other presentations, which will be similar to lab, but as we've been doing for the rest of the semester, you don't actually have to come to lab. So I'm hoping that'll relieve a little bit of anxiety and it'll help me see what this would look like if we did this with an online group. So I apologize for the experimentation, but again, I hope some of you will find this actually be an improvement over having to come into the lab and present in front of your whole lab. So that's the way we're going to try it. Hopefully there won't be too many speed bumps. And then there's the final exam. So then the Thursday of next week, that's when we'll have the final exam right here in this class at the normal time period. And that'll be this 75-minute exam. It'll be cumulative, but of course there'll be more of a bias on the back end of the course. And then I will try to get, so that'll be on Scantron, just like the midterm. So I'll try to get results back to you as quickly as possible. And then on the Tuesday of finals week, if you'd like to come in for a retake, then that retake will also be available. Just like the midterm, it won't be the same exam, but it'll be the same length, and it'll try to be where every question is the same difficulty or very similar content. So if you don't want to come in for one and only come in for the other, that's fine. If you want to come in for both, that's fine. Your score on the final exam will be the max of the 2. So any questions about this layout? Yeah.
So then will we probably have our final course before the second?
Yes, yes. So that is, I want to make sure that everybody knows how they're doing, hopefully before the final exam. So that, I mean, there might be, of course, the reports, like the final reports, I can't get those back to you, so that'll probably take, until the end of the semester, just because those get turned in on Saturday before finals week. But the outstanding homeworks, and the outstanding labs, then those should come back to you before your first exam. That's the goal. Yeah.
On the video presentation, so do you want us to do like a voiceover, or do you actually want us to like physically be in front of the video camera talking?
Whatever you feel would be the best way to make your argument. So I want you to sort of make use of your team, and I've mentioned this in the rubric. By make use of your team, that doesn't mean everybody's got to have 2.5 minutes of the 10 minutes. But it has to be sort of like, wow, that argument flowed better because they flipped from this person to this person. And even though this person didn't say that much, they really had an expertise in the simulation or whatever. And so if it works best for you, saying I want to stand in front of a green screen or something like that, because there are apps out there that will allow you to subtract that, then that's fine. Or if you would rather just have the 3 or 4 of you stand in front of a webcam, and or even if I don't see you, if I just see the slides and I just hear the audio overlay, that's okay with me. And if you would like to make it not just slides, if you'd like to sort of then Alt-Tab into Arena and show actually your simulation, that's fine too. So you've basically got 10 minutes or less, and less is always good, to make an argument, and however you think would be the most effective way to make that argument in a video format. All right, any other questions? Okay. And then like I mentioned, that the course evaluations should be available. They're available, I think, until before finals week. So I'll probably send another reminder about those. Now let's do a quick attendance exercise for today. So just to jog everyone's memory, so we've been talking about variance reduction techniques for Unit K all last week. So obviously the short-term goal of variance reduction techniques is to reduce variance. It's right in the name. But what's the ultimate goal? Why do we care about reducing variance? So in your sort of attendance exercise, and feel free to chat with your neighbor, I'm sort of wondering, what is the ultimate goal of VRTs? Why do we bother with taking the time to reduce the variance in these? What do we hope to get out of it? When we're doing simulations, why do we care about reducing variance? What is that bias? What's the benefit? And this is something that if you were to look up variance reduction techniques, like if you were to look up common random numbers, then you might find that the definition will say like, oh, this method reduces variance. But they don't often say, well, why is that a good thing? So that's what I want to make sure you understand, is why is that a good thing to reduce variance in a simulation output? All right, so anybody have any good answers? What's the point of VRTs? Why do we reduce variance? What do you get out of it? Yeah.
Get a small confidence interval.
Yeah, so that's one thing, to get a smaller confidence interval. But what's the sort of other half of that? So like, it's always good to get a smaller confidence interval, but and reducing variance gets us a smaller confidence interval. But I guess the key point is that like there are two ways to get a smaller confidence interval. You can either reduce your variance or you can do something else. Yeah. The number of replications, that's right. So the major point here is that we do want to reduce our confidence interval size. That's the ultimate point. That is a good point. But we either have to pay for it by spending, an hour on a sim instead of a half hour. Or if we design the experiment right, we can stick with a half-hour simulation and get narrower confidence intervals. So it's to reduce the computation time. And so that's kind of the goal here, is that how do I reduce variance so I can get fewer replications, so that I can go from hitting play in that batch run and having it come back after a minute versus having it come back almost instantaneously. So that's what we're kind of going for here. Because in order for you to find very tiny effect sizes, it may require running lots and lots and lots of sims, unless you're very clever about how you design the experiment. And that's what we've been kind of going through here, how to build these controls and these designs. So we control for additional sources of variance so that we can focus, like a laser, on the differences that come out of our sims and not out of artificial things like, I was just unlucky in the random numbers that I drew. And so we talked about 4 different ways we've been doing that. And so these are the most common VRTs. There are more. And so just going to kind of give us a quick review, but these 3 up here are sort of catered for simulation because they really require reaching into your simulation and tweaking the random number generators in some strange way. But this last one, control variates, really can apply to real world experiments as well. So really any experiment where you are interested in one thing, but are seeing a variance on your output that could be due to something you're not interested in, you can use the method of control variates to subtract away the things that you're not interested in, so you can focus on just the thing you're interested in. And so I'm going to summarize that in a second. So just to show these a little more graphically, so with common random numbers, the idea is I choose one single random number seed, which I can think of as like a 20-sided die that always comes up with the same pattern of numbers. And I can run that into 2 different simulation models. And because I've controlled the input variance so that the same inputs go into both, then my hope is the difference that I see is actually going to be more representative of the difference between the simulation models than the difference between just the inputs that I would have put in if I put independent inputs into both. So the idea is I take one random number seed, I get one difference out, and then I can choose a different random number seed, which is, again, it's like another 20-sided die that comes up with a different sequence of numbers, but it's always the same sequence over and over and over again. I run that into both, and I get a different difference. But again, I hope then that this difference really captures the difference between the models as opposed to the difference between the random number streams that went in. I could have taken the random number stream from the previous slide and put it into A, the random number stream from the previous slide and put it into B, and then I would have 2 sources of variance, the inputs as well as the models. By using common random numbers, I only have 1 source of variance, and that's the models. And so that's how we've reduced the variance. So I'm going to do that over and over again. I get a bunch of different seeds, and those come down to my replication pairs. And for each seed, I have a difference. And now these data right here, I can generate a confidence interval from. So I can say, is the confidence interval that captures this column significantly different from 0? And if this confidence interval is greater than 0, then I can conclude that, say, simulation A is better. If this confidence interval is less than 0, then I can say simulation B is better. If this confidence interval captures 0, I still haven't really identified which one's better. But if my confidence interval is really tiny, then maybe the difference between them can't be that large, and maybe it doesn't matter which one is which. So if you can say, sorry boss, I don't know which operational model is better, but I can tell you that their performance can't be any different than 1 minute or 1 person or $1. And your boss comes back and say $1, I don't care about $1. So then in that case that you just pick one arbitrarily, because even if it's suboptimal, it's not really enough to make a difference. So that's why one of the reasons we reduce variance there is to get us these tighter confidence intervals with the same number of replications by removing extra sources of variance. So I guess before I got it, so any questions about CRNs? This is the one that we've seen periodically, yeah.
Just a quick question. Did you say that we only use 1 seed or multiple seeds?
Multiple seeds, so 1 seed per replication.
Okay.
So you have a replication that goes into, so it's a replication of A and a replication of B. The downside of common random numbers is that I kind of am locked into an even number of replications. I have to run the simulator twice. But I mean, I could generate all the numbers once and then save them and then use them the second time around. So it's not necessarily more computationally costly, but it might be that if I would have run these things independently, A might have naturally had less variance than B. And so it's possible that by running independent replications and then using like a Welch's 2-sample test, then I might have actually been able to use fewer replications to get the same result. But most of the time, running A the same amount of time as running B and running the same inputs into both is going to actually give me less variance in the difference than running them independently. So any other questions about CRNs? So on the final, you might imagine, like, say, well, how can I combine things from pre-exam and post-exam? Well, you can see I'm mentioning random number seeds, and you can see these uniform random numbers coming up. And so you remember that uniform random numbers, we pipe into inverse transforms, and then from those inverse transforms, then those end up being our samples of our inputs we run in the simulations. So you could imagine me asking you to do an inverse transform problem like those things you did for the midterm, but then I might add a twist that I'll say that, well, but I want you to use common random numbers to compare, let's say, 2 inverse transforms. And so you would have to know that you run the same random number into both and then compare the output. So as opposed to running a random number into one inverse transform and a random number into the other inverse transform and comparing the independent ones. So that's kind of an example of how I might combine the pre-midterm and the post-midterm material. All right, so antithetic variants, this is out of order from how I presented it last week, but I'm grouping these together because these are the ones that's easy to get confused. And so antithetic variants are very similar to common random numbers, but we're focused on absolute performance instead of relative. So the idea is I have one simulation model, and I want to be able to get rid of variance that has to do sort of with like the order of execution. So if I just ran independent numbers into one simulation model, I might get a string that are above average before I start getting a few that are below average. And so I need a huge number of them to balance out all the above average and below average. So the idea is there a way for me to doctor the inputs so that for every time I run the simulation one way, I then the next run, immediately next run it a different way, so that I'm more likely to get a counterbalance to whatever the output is, so that I can run fewer replications, and each replication will hopefully have a pairing replication near it that when I average the two together, then come close to the average I'm trying to estimate. And so that's the idea of antithetic variance. And so you draw the random numbers once up here, and you get a set of U01 random numbers. And then you create antithetic pairs, which are just 1 minus all of those. So 0.25 becomes 0.75. 0.8 becomes 0.2. And then I can run the simulation model again, but instead of calling the random number generator, I just use these as my random numbers. And I run that in, and then I get 2 different outputs but these are not independent outputs, so I can't view them as independent data that I can put into a column and take a confidence interval of. I have to then aggregate them into one average, and then the averages from pair to pair to pair to pair are independent. So this is my one random number seed, it generates this one average. If I grab another random number seed, it's going to generate another set of numbers, another set of antithetic numbers, another antithetic variant over here, another average. And then I put those all into a table, and seed, 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 seed. Each seed has each one of these differences. And then again, I can calculate a confidence interval here, and that gives me a confidence interval on the absolute estimate of performance for the one simulation. So if I want to know, I think that this simulation model should give me a average wait time of 5 minutes per customer, then then I look down through here, if 5 minutes per customer is not in this confidence interval, then this sim probably needs to be calibrated. This sim probably needs to be adjusted, needs to be fixed, because it is not producing the 5 minutes that I'm expecting from the real system. But if 5 minutes is in this confidence interval and the confidence interval is small, then I've got pretty high confidence that this model is a good replica of the real world system. So, are there questions about antithetic variants? And I can put up this sort of picture here, comparing to the common random numbers. Yeah?
So how do you generate the confidence interval for is it two separate confidence intervals, or?
No, it's just one confidence interval of this column of averages. So if I were to do that, I might see something down here that would say it went from 4.7 to 5.25. And so then that confidence interval, that would be an estimate of my average wait time. And then I could say then anything in between that, I can't really tell if the simulation's any different from that. But if I'm expecting something outside of that confidence interval, then my sim isn't producing it. And I need to go back and see, like, what am I missing in my sim? Or the other way around, if I've already validated my sim, and I've made a change to my simulation model, like I've added another server or something like that, and now I want to tell my boss how much performance have I improved by adding another server, then I can give my boss this confidence interval and say, your new performance, it was 5 minutes per customer in wait time, now it's somewhere between 3.6 and 4.2. And so then your boss can say whether or not that's a good enough improvement. So any questions on AVs and their difference from CRNs? And so again, you could imagine me asking questions where I give you a string of numbers, and I give you an inverse CDF, and I then ask you to use the method of antithetic variance to estimate the average from that from whatever that CDF comes from. So if I give you the CDF for an exponential, and then I'd say, well, let's say you wanted to better estimate the average of this exponential, then you would have to know that you would put in that if I gave you this string of numbers, you wouldn't put in these two numbers, you'd put in this number, and then you'd also put in this number that you'd have to calculate. So if I told you to use antithetic variance, then that means that I'm expecting you to generate pairs where your first one comes from the list of random numbers I give you, and the second one comes from 1 minus whatever you used in the first list. And you go back and forth and you create averaged pairs across that. Yeah.
So for the column of all the different, so for that, when you have the confidence interval, do you compare that with the real world system, or do you compare it to the different replications that you did in there?
Well, so the replications that you did are sort of what generate each one of these. And so like I ran these two antithetic replications here, and it gave me this average. I ran two more and it gave me this average. This confidence interval here, I would normally compare to the real world, either to say whether my model was accurately representing the real world, or if I've got a model that I've already validated, then to say that my model, when it's been implemented with an operational change, I want to sort of estimate how well the operational change improved or not the system, and this would be capturing that. So the confidence interval is sort of, I guess, outward facing. Yeah.
So for like this method, would you report the result as a list of like R and then like as pairs of like R and then one line?
No, this is sort of what you would have in your Excel spreadsheet stored in a data set somewhere, but then what you would report is the confidence interval from this column. So we'd say we estimate the average waiting time to be, and then you give this confidence interval. Or a lot of times what people like to do is they would estimate, they'd put the point interval, like we'd say 5.1, and then they give a confidence interval of, whatever, 4.9, comma, 5.3. And then you would say somewhere that that is a 95% confidence interval. And then that really helps them, because then you're, this sort of gives people something that they can talk about in shorthand, but then when they want to understand the uncertainty in your estimate, then they can look here and they'd say, well, so it can't actually be 5.1, but it's probably not 4.8 or 5.4. All right, any other questions about AVs or CRNs? All right. So I'll skip that for now. All right, so then linking back. So industrial engineers, you're probably very familiar with the general philosophy of Six Sigma. So Six Sigma, is about reducing your amount of failures to a point in which they are in a tail of the distribution of things that can happen. Way out in the tail, 6 sigma away. When we talk up about ourselves as engineers, we say we're improving things so that we get to the point where those failures are 6 sigma away. In the real world, it's often the other way too, where if you're saying, if you got 7 sigma performance and somebody can go back and say, why 7? Can't we cheapen this process and make it 6? So it's so this ends up being a way in which we regulate the quality of our products. But the point here is that it's not infinity. It's not ever infinity. There is no way to engineer away failure. There's only ways to use trade-offs, costs and benefits, to end up pushing them into tails. But they're always going to happen. And so the question is, how do we know, for example, in a complex system that we are 6 sigma away? And how do we figure out when a simulation generates a rare event that it's something that we need to worry about or not? So that's kind of where this importance sampling comes into play. So on a computer, you get a funny result, and then the question is, do I need to report this up the chain? And so, there are all sorts of examples where, this is an example people probably don't know as much about, but one of Samsung's many recalls is this on these top-loading washers. And so these are washers that came out, and it turns out that due to how things were sort of bolted together, this drum at high speed could actually launch out of the washer, and you can see there's a dent in the wall if you look at the slides online. And it would hit people in the head. People got major injuries from this effect, and it was just because there was a vibration that was slightly outside of spec as to what the latches on this lid could handle. And when you got into the random, this tiny little rare event, then you could pop this thing off and the drum could come flying out. And so you could say, well, it happens. It's a rare event. Every, this computer at any particular time could break, could burst into flames. And does that mean that we should condemn all of products by this manufacturer or that manufacturer? And so, one event doesn't necessarily mean that your engineering has gone wrong, but when it's so many that multiple people, start having this, even if it's only a few, it starts getting press. So if you're a company as big as Samsung, and even 3 customers get hit in the head by a drum that comes shooting out of their washer, then that ends up looking really bad for your brand. And they had to go through a major recall, and they claimed before they even did this recall that this is extremely rare, and people don't need to worry about this, and as long as they wash their bedding on a particular setting, then it shouldn't be an issue. But people didn't like that idea that if you used it in a way in which it appears like you could use it in potentially, even if it's rare, this could happen. And so accurately estimating how rare this was something that apparently Samsung missed out on, and it it ended up costing them a lot of money. You might be more familiar with this case. And so, the Note 7. So for a long time, you couldn't even bring a Note 7 onto a plane. And because this would happen. So this is a cell phone, and this, was its battery. And so these batteries would end up bursting into flames inside people's pockets. Again, very rare. So rare that, Samsung would say, you don't have to worry about this. But common enough to be caught on camera, to be spread around in all of this news, to the point where, again, the FAA says, we're not even gonna let you bring it on planes because it is just frequent enough, even though it is infrequent for us to worry about. And it's just, it just doesn't look good. So, estimating these things becomes important. And coming back to simulation, this is much more recent, of course. So the MCAS, anti-stall system, in the Boeing, the MAX here, this was, an example of a system, an automated system, that under certain conditions, when trying to do the correct thing, would actually end up leading to a sequence of events where the plane would end up bringing itself into the ground. And of course, there were some, there were two catastrophic outcomes of this. And in the end, when people looked at the records here, then they find that there were pilots in simulators that actually experienced this failure condition and wrote it up. And so, but then the question was, when does this failure condition reach the point where you say, oh, your simulations, they can crawl through a whole bunch of outcomes that may not be realistic, that may be pathological, so maybe we don't need to worry about this. So how do we really quantify when a simulation shows something catastrophic that we should actually report it up the chain and make some major changes to a real system? So that's one of the ways in which importance sampling helps us with this. Because the problem is that if these really are super rare, it may take lots and lots of simulation runs in order to experience them even once, let alone quantify how often they'll occur. And so rare events are important. Estimating the frequency of them is difficult to do. Even in simulation, but that's ideally where you'd like to do it, because you'd like to not actually experience these events in the real world. So how do we trust our estimates without having huge numbers of replications? And that's where this kind of mysterious thing of importance sampling comes into play. And so the idea here is, if I have an input like this one, I might just happen to know that the only time I get these catastrophic events out of my simulation is when the input are in these really weird cases. And so the input model might have to do with how that drum is spinning in my simulation. That input model might have to do with weather conditions and how it's actually interfacing with the plane. And so these are rare, and they might be difficult to find, but you might have an idea that they're probably living in this tail out here. If I just simulated a normal washer, a normal 737, then I might have to wait for millions and millions of simulations in order to experience these out here. But the idea is, what if I can take my fair die and I can make it loaded? So guaranteed to roll 7 or 11 every time. So maybe if I can manipulate my random numbers, I can actually end up making all of my simulation runs exist in these terrible conditions. So it's like, this is like making the pilots always fly through, thunderstorms or something like that. And now the question is, if I want to estimate back into, so how often, like I know that if the pilots were always driving through thunderstorms, that they would always have, more problems than normal, but then how do I go back and then estimate what it would be like if they were running through the normal input distribution here? And so the idea here is that I can use mathematics. If I know this distribution, the typical distribution and the atypical distribution, then I can simulate under the atypical distribution and then use a fancy ratio, we call a likelihood ratio, to rescale my outcomes so that the many interesting outcomes here turn into a smaller frequency here, but a very accurate one. And so to see that more concretely, then we can say, going back to this kind of graphical view here, I can run R different replications of one simulation model, and they all have these different inputs, and these are kind of typical inputs from a typical probability density function, and they have typical outputs over here. And so these here don't include any of my catastrophic outputs. So the idea is what if I then put in pathological input data, so that now I get, if these were inter-arrival times, then now maybe these are, I've now made everyone have a very small inter-arrival time in between each other, which might be very rare in the real system. But I'm just going to simulate a world where that's the only thing that happens. And then I generate a lot of outputs, maybe a couple that are still typical, but a bunch more that are atypical, a bunch more of the interesting outputs that I care about. And then I can see how frequently they occur in this bizarro world. But then as long as I can transfer bizarro world numbers back to real world numbers, then I can take the frequency that I've estimated here and turn it back into a normal frequency. And that's what we do in this sort of case here. I generate a pathological replication with a pathological output. I ask if that output is interesting or not, and then I weight those ones or zeros by this likelihood ratio. And that likelihood ratio is just the PDF of what I would have gotten under a normal simulation divided by the PDF of my input model under these weird conditions. And that ends up giving me, instead of ones and zeros, fractions down this column here. And so by doing that, then the confidence interval that I get out of here will actually end up being, whereas the confidence interval from this column would be the fraction of events that occur in bizarro world where everything's terrible. In this case, the fraction of events in this confidence interval will be the real world frequency, how often things occur in this world. And so and that's what I can use to then generate a confidence interval to report up to my bosses and say, this weird event that we're trying to estimate, by using importance sampling, we were able to simulate in a week instead of 10 years, that we are going to occur, 1 out of every 3 billion models is going to have this problem. And then you can start asking, now, is that a rare event that is sufficiently rare for us not to worry about? So that's importance sampling. It's a little mystical and magical, and it's something that we can only do in simulation because we have to transport ourselves into a universe where things are always bad all the time. But because we can simulate that world and we know how to map between those worlds, we can then take insights from that strange, strange place and actually use them to inform things in our world. So are there questions here about that importance sampling, this approach of biasing your input models to be incorrect?
Wait, so why, after you get the output from your simulation models, do you transform it to normal again?
Well, it's because the inputs that went into generating the pathological outputs are the wrong input models. So you might have estimated your input models like let's say you were modeling, Noodles and Company or something like that. And so people are coming into there with a particular inter-arrival time, and you say that on average people arrive, 1 every 30 seconds. And so you decide, though, that you're not going to use your input model. You're going to remember that that's the input model. And instead you're going to use an input model where everybody arrives in a normal distribution that's tightly packed around 5 seconds or something like that. So that would be a terrible, terrible thing under normal operations for people to just be coming in continuously with only 5 seconds between them. But that's what you're going to simulate, as if that was your input model. So you've transferred yourself into a place where Noodles and Company doesn't ever get a break. And then you say, how good is your performance? How often do you violate our performance criteria in the weird world? And then so if you were to estimate this column, it would be meaningless because Noodles would come back and say, oh, garbage in, garbage out. You picked a really bad input model, so how can I trust this? And so you come back and say, yes, although I picked a bad input model, I know the relationship between the bad input model and the real input model, and I will use that relationship to convert these data into these data, and these will represent the estimated times that you'll actually fall into this failure mode in the real world. So the path that I didn't kind of show here is like the transformation into Bizarro world, and then because I'm in Bizarro world, I have to come out before I can make any interpretations. So any questions about importance sampling? All right. So last overview thing here, control variates. That's the last way that we talk about in this class. It's also very common, and this can be used in real-world design of experiments as well. So the idea here is I have two models. I've got a model I've implemented. If I go back to the noodles example, then this is noodles with one cashier. This is noodles with one cashier and a kiosk or something like that. So I've got these two different models that I'd like to compare. And I might use common random numbers to send the same inputs into both. But maybe and that would be an input that I can control easily. But there might be something that I can't control. Like maybe for some reason the temperature of my laptop is affecting the way in which numbers are generated. Or maybe I'm doing this in the real world and the temperature of the day actually affects the way people arrive and how quickly orders get made. And so if there is a real world input variable that is difficult to control, meaning I can't send the same one into both, but it's easy to measure so I can see what ones go into these, then the idea is control variates will say, since I can measure this variance, I can subtract it away so that the only variance left is the variance in between these two models. Because really what I care about is how the operational strategy differs between A and B. I don't care about how this temperature or whatever this other effect is on my output. But I know that they both are going to affect this output. So the differences I see here are in part due to the operations and in part due to variables that I can't control. So if I can't control them on the front end, I try to control them on the back end by subtracting them away. That's the way I can apply control variates to relative performance. It's going to be more common to see control variates representing absolute performance. And so I've got two replications of one simulation model, and I'm trying to estimate a performance variable. And I run in, so let's say these are inter-arrival times going into one, and these are inter-arrival times going into another. Now I know that I designed this random number, I designed this input model to have an expected value of 5 minutes. But I just happen to know that by random chance, when I look at the 100 or so customers that I simulated, then on average, people arrive between 2.3 minutes. Just when I took 100 samples from this distribution, I just got unlucky and they arrived a little more quickly than usual. But in this replication, when I use a different random number seed, then they actually arrived with more distance in between each other. So in principle, I can now label this is kind of like a difficult case, and this is an easier case. And is there a way in which I can use this measured difference to reduce the variance in the output so that I really focus on an actual good estimate of the performance variable without running a lot of replications? And so the idea is maybe I could subtract this from the average and then use that difference to modify this output. And then maybe I could subtract this from the average and use that difference to modify that output. The last kind of use case for that is what if instead of this case here, I've got just a single input coming in, like the temperature of a nuclear reactor or something like that. And on one day it's this, on another day it's that. I know the real average in between. This is supposed to have an E here that's not rendering here. And so the idea is, can I end up subtracting again this difference and this difference and use that to modify these outputs so that I get less variance in the output, so I can estimate a smaller confidence interval with the same number of replications. So the way that will end up looking is I will end up taking stats on both the input and the output before I calculate this confidence interval every replication. So the idea here is I'm going to take my stats on my input and the covariance between input and output, and after my entire experiment is done, before I calculate my confidence intervals, I will take every output that I measured and subtract off a tiny little fraction, which will be proportional to how much the input differs from its known mean. And if we end up asking for what the right value for that is, we can solve for it mathematically, and it's this formula where it's just the covariance of the two divided by the variance of the input. This just captures how much the variance of the output is represented by the variance in the input. And by plugging that thing in, I get a formula that looks like this one. So if I measure this after my experiment is done, the variance on the input, if I measure this, which is the covariance between the two, and this, which is the variance on the input, then I can end up modifying every single output that I measured to generate a new set of outputs over here that hopefully has smaller variance. And so that the mechanism there is if I just unpack that variance, then basically I've got this term here converts the standard deviation in units of x to standard deviation in units of y. It tells me how much variance I trade from x into y. And then this gives me a z-score from the input. So this is saying for this input is really far from its variance. So I'm going to end up getting the entire amount of conversion factor. Or if this input's very close, then they'll end up saying, well, actually, this is right on its mean, and so this output is pretty much not getting affected by the input. And so with all of that, I can end up generating these outputs just by these steps here. So summarizing that in a table form, I run my experiment with, say, 100 replications. I've got all of these inputs, I've got all of these outputs, and so I can calculate the mean input, the variance on the input, and the covariance between the two, the correlation between the two. With that, I can then generate a new set of outputs, which are just simply the old outputs modified by that formula that I showed. And then with those new set of outputs, I can calculate a confidence interval. And so the confidence interval on the original output goes from -2 to 25. The confidence interval on the control variant goes from 3 to 20. And I know that both of those have the same mean in population terms. And so now I've managed to get a smaller confidence interval. And so, just to wake everybody up a little bit, so if I look at this confidence interval, how many people by hands say that this confidence interval indicates that P is less than 0.05 if I'm comparing to 0? How many people say that this confidence interval indicates that P is greater than 0.05 if I'm comparing to 0? All right, let's try that again. Comparing to 0, so hypothesis of 0, my output is 0 here, that's what I'd like to test. And I'm now looking at this confidence interval. So the question is, in looking at this null hypothesis, that the expected output is 0, if I get this confidence interval, is my p-value greater than, how many people say greater than 0.05? How many people say less than 0.05? All right, so then I'll give an answer in a second. Then if I look at this one, so well, actually maybe we'll go over this. So here, if I see that 0 is in the confidence interval, that means I cannot tell the difference between this output and 0, which means I cannot reject the null. So that means that P is greater than 0.05 in this case. So when the null is in the confidence interval, your p-value is greater than your significance level. And so that's what this summary tells me. You would just report this confidence interval, and your reader, who is an educated statistician, would look at that and say, I see that your output is not significantly different than 0.
So generally speaking, like as long as it's in the interval, you have no reason to like reject it.
That's right. You have no reason to reject it. And you can maybe use the width of the confidence interval as a surrogate for power, where you can say, I can't reject it, but I know that it's probably, that the real value is probably not 50. The real value could be anywhere from -2 to 25. I can't reject 0, but the real value is probably not 26. So now that we've all had that kind of brush, now let's look over here. The control variant, remember, it's the exact same data, but I've just subtracted off a tiny little bit that had to do with the statistics from the variance in the input. And now I get this confidence interval. So if I look at this confidence interval, and again I'm testing to see whether this thing is equal to 0 or not, So if the null hypothesis is equal to 0, that's the hypothesis we're testing, how many people say this confidence interval indicates a p-value less than 0.05? All right, how many people would say this confidence interval indicates a p-value greater than 0.05? All right, so now it looks like we got a more consistent answer that this would be less than 0.05. And that's because the 0 is outside of that. So it just goes to show that even though I did not run any more replications, I went from not being able to make a difference or tell a difference between the output and 0 to suddenly being able to discriminate quite a bit more. I really brought that confidence interval in so that I could now reject a lot more hypotheses. And if 0 just happens to be an important one, then now I can actually reject 0. So this general method, if when you apply to non-simulation studies, is when you start getting into generalized linear mixed modeling. And that kind of is a linear modeling framework which incorporates like all of this stuff, elements of common random numbers, elements of control variance, all together, so that it naturally factors out all of the sources of variance that you don't care about, so that you can zoom in on only the source of variance that you do care about. So in this particular case, we had inputs that varied that we could not control for, but we could measure. We knew they had an effect on the output, and so we just subtracted off their effect. So the only effect that was left over was the effect of the actual model. And so now that's what allowed us to then tighten this up. Any questions about this approach, control variance? All right, so let's do an attendance exercise then. So we just went over 4 variance reduction techniques. Feel free to talk to your neighbor. I just want you to sort of make sure everybody's test your recall. Which variance reduction techniques generates inputs that are purposely biased to greatly increase the number of normally rare output events? So of the 4, which one biases the input models to be artificial input models to produce more rare outputs than normal? All right, so how many people say common random numbers? How many people say antithetic variants? How many people say control variants? How many people say importance sampling? All right, importance sampling is what I was looking for. So importance sampling is the one, has this funny name. You just have to remember, rare events are important. So importance sampling is sampling from input models in the kind of important regions that allow you to zoom in on the events you care about. So in this particular type of simulation, you don't care about the typical outcomes. You want to know how often the rare things occur. And this is generally in a realm of Monte Carlo sampling. All right, so course wrap up here. So basically, then this course is a simulation course, a stochastic simulation course. There are sort of 3 big branches of simulation that we talked about back in lecture A2. Agent-based modeling, system dynamics modeling, which is the main focus of 477, and SOS 212, which I teach in the spring, and then this course, this 475, discrete event system simulation models. And so those are, again, the 3 basic simulation frameworks, and then within them there's a ton of different software packages. Question?
Is there an agent-based modeling class here at ASU?
Well, that's there. Occasionally, a guy named Marco Jansen teaches an agent-based modeling course both at the undergrad level and the grad level. I don't know how often he teaches it. It used to be a SHESH course, and now I think it's a SOS course. But if you're interested in agent-based modeling, I would look up Marco, and I think on his course webpage, he actually has, I think he has even a textbook, a free textbook that he's written that he uses for that course. So you could you should at least find info on the course, and if not, when it's taught. So that's a good question for AB. And occasionally also the Complexity Institute here at ASU will run workshops in agent-based models that are open to undergrads, and sometimes they cater lunch and things like that. So So that's a good question. So mainly been focusing on DES. In all of these packages, though, you're going to find a ton of different software. So we, of course, have been using Arena, which is primarily for discrete event system simulation. You're going to go out into internships and jobs, and they're not going to use Arena necessarily. They might use Simio. FlexSim was popular, and they're going to ask, oh, so why didn't you learn FlexSim or something like that? And there are all sorts of historical and inertia reasons why we use one package. If we were to have used Simio, so the guys and gals who created Arena, when they left Arena, or when Arena got sold to Rockwell, I think, then they end up spinning up Simio. And so Simio is kind of like Arena, part 2 or something like that. It's very similar, but some people say that it's actually kind of gotten more advanced. And so a lot of people say, oh, why don't you move into Simio from Arena? And I'd say, why don't you rewrite my labs for me? But then there's a lot of others. So we purposely want the IE students to have the potential to have a bite in multiple programs, which is why in 477 we use AnyLogic. AnyLogic also is a competitor to Arena. AnyLogic does not only the type of sim in 477, it also does the DES simulation modeling. We could have used AnyLogic in this class as well, but we wanted to at least have people to have the potential to see too.
How popular would you say ProModel is?
I would say there is, it's hard to say, because there are communities that just live and die by some of these, and within those niche communities, then you find that there's just a huge representation of one. And if you want to work in that community, then that's the one for you. But then if you back out and look at all of simulation, it just gets lost in the mix. So but it is definitely popular. It's very powerful. They all got pros and benefits. But I don't want you to view 475 as being the Arena class. But I hope it's more general. And because I think that this general plan applies to regardless of what simulation framework you're using, regardless of what software framework, and this is what we've tried to follow throughout the course. And so basically problem formulation, so learning about probability, input modeling, things like that, data collection and model conceptualization, translating your model into computer code and doing V&V on it, and then finally the experimental design and the simulation run. That's kind of the stuff we've been talking about last week. And then finally, what you're doing in your final report is implementing and documenting. So when they say implementing here, that means actually going out in the real world and making a change. But you're kind of getting almost there by you'll write a final report up. And you should think of your final report in the kind of frame as if you're giving a report to a stakeholder who could potentially make changes that are informed by your simulation. Now, your simulation might find that all of the crazy ideas you had were crazy ideas, and you should never ever implement them. And that's fine. You just need to say that and justify it. Like you could say, well, we thought that by putting all of the employees on one side of the store and having all the food on the other side of the store and making them go back and forth all the time, that there would be an improvement in wait time or something like that. But it turns out there wasn't. And that's fine. You just then show me that, rigorously that there wasn't. Like, here's my confidence intervals. And it turns out that this actually was worse in performance and not better in performance. And then you could say that. And so implementation sometimes means not implementing. But that's ultimately where all of these things should go. And so that's kind of, regardless of what package that you'll end up using in your careers, my claim is you'll follow all of this through. There's going to be aspects of all of the kind of experiments you've done in Arena, but maybe in a different software package. But the main thing you should be considering whenever you're writing these things is the model illuminating and useful? And that is really focused again on this documenting, reporting, and implementation. Could you, after you were done running the sim, did you learn something? And could the thing that you learned, if you wrote it up and gave it to the right stakeholder, be implemented and make a change in the world? And if you can't write up something interesting that said that you learned, then maybe your simulation model wasn't quite as rich as it should have been. So that's what we're kind of looking for is, did your simulation teach you something? And so with that in mind, you've got your project presentations next week, the sort of the virtual ones, the final report due that Saturday, as well as your peer reviews of the other peer presentations, and then the final exam, starting next week. And then, by the way, if you're still, thinking about courses, and again, 212 and 598, be interested to have you. I have had former 475 students in this in the past, and it seemed to work out okay. With that, are there any final questions before we just do review stuff and presentations next week? Yeah.
Can I ask a review question?
Sure.
Can you clarify, or can you give like specific examples of how you use verification and validation?
Yeah, so the question was effectively the difference between verification and validation. So that's a good question. So I talked about V and V, came up on the previous slide, verification and validation. Verification is debugging your code. It's verifying that the code you've written captures the conceptual model that was in your head. So it basically says, I wanted an exponential with a mean of 5. Did I actually implement an exponential with a mean of 5? And so I might run my sim, and I might take data on the exponential that I generated and make sure it's a mean of 5. If it doesn't have a mean of 5, I wrote something incorrect in my code. Once you've verified your code is doing what your head is doing, validation is then saying, does your simulation model actually match what the real world is doing? And if your simulation model at that point doesn't match what the real world is doing, then you need to update the model in your head and then update the simulation model. So verification is about debugging, validating is about linking back to the real world it started with.
Calibration.
And calibration is the whole process of improving a model. If improving, so it comes from the word caliber and quality, so it's improving the quality of a model. It's the iterative process of V&V over and over again. Any other questions? All right, so last attendance exercise, and then you guys are out of here a little early. There is, I believe, an IISC luncheon on the 6th floor of the Brickyard, so for those of you that need a reminder for that. But just basically, do you feel prepared for your final project presentation next week? That's all I want to know, just kind of curious.
Not at all.